I welcome you to this video presentation on robust resource demand estimation using hierarchical Bayesian model in distributed service systems. My name is Sumanta Mukherjee. I am a research scientist at IBM. In the next few minutes, I will share our work in the area of resource demand estimation. I will start my presentation with an example that has motivated us for this work. Extreme weather conditions are a big challenge to electrical distribution grids. Every year, a large number of blackouts are caused by storms alone in the United States of America. Smart grid-based automated solutions allows remedy to non-weather related local network failures. But large-scale disruption due to natural calamities requires manual intervention. Electrical distribution grid spans over a large area, serving billions of customers. Every year, in the United States alone, weather-related outages affect millions of customers. Over the last 2 decades, the incidences of outages due to extreme weather events are showing an increasing trend. Fast power restoration post-extreme weather event demands proactive response. Proactive response requires resource preparedness. Resource preparedness is a process to ensure the availability of sufficient resource at all times to attend to the demand. Effectiveness of the resource preparedness relies on an accurate forecast of resource demand. In an electricity distribution grid, for an upcoming storm event, an accurate estimate of the total man-hours required for the restoration work with a spatial resolution is essential for the proactive resource allocation decision. This poses a multitude of challenges. External factor influence, insufficient data, demand heterogeneity over spatial distribution are few in the list. Before we delve into the problem and details, let us discuss few key concepts: service request, task, activity, and demand. In electricity distribution grid, service requests correspond to the number of reported outages. Tasks are analogous to resource assignment. Multiple tasks may together resolve a service request. Each task may involve many distinct activities. As an example, to attend an assessment task, an engineer needs to travel to the location, then perform an assessment task at site. These are two distinct activities associated with an assessment task. A demand is defined in terms of man-hour. Each activity completion requires specific man-hours, and they together describe the resource demand to attend a task. Various process variables influences final resource demand. We call them factors. The factors are of two types: external factors and internal factors. External factors are not associated with the process. Weather, location, time of the year are examples of external factors. Internal factors are associated with the process and known only at the time of execution. As an example, task type, namely assessment or repair work, mode of transportation to the site, electrical devices associated with the power failure are examples of internal factors. It must be noted, internal factors can be associated with a service request, task, or activity. The causal dependencies that restrict factors influence order, as shown in the figure. In this work, we proposed a process template-guided, data-driven forecasting model to produce an unbiased resource demand estimate, given an expected number of service requests. A various external factor influences the final demand estimate. Thus, a system is described with such observed factors. We have used historical service logs to train the demand forecast model. Here in this slide, we summarizes the compositional association between service request, task activities, and demand. Our proposed approach explicitly models this compositional structure. Each service request can be grouped into different request types. As an example, in electricity distribution grid, depending on the type of device associated with the failure, a service request can be further grouped into service request types. The classification into request types are often associated with distinct operating characteristics in the demand response. Each service request resolution involves one or more tasks. We explicitly perform task modeling in our proposed solution. Each task is a set of predefined activities. Resource demand associated with each activity types are distinct. Process operating characteristics is another key concept we have introduced in this work to achieve a low variance demand estimation. The operating characteristics is a factor-driven subsystem identification that exhibit distinct demand response distribution. If there exists a distinct factor value that partitions the data into groups with distinct and tight demand distribution statistics, we refer each such partition as a process operating characteristics. The solution involves various modeling components. At first, we discover all influencing factors from the historical log data. The factor influences are measured using normalized mutual information scores. From the same service log data, we further discover all process operating characteristics for every activities. For each operating characteristics, a factor dependency graph is derived. Factor dependency graph ranks the factor by their ability to explain the discriminatory demand behavior. The factor dependency graph is further used to produce hierarchical Bayesian model for the demand estimation. Conditional task models are trained independently. We have used finite chain Markov model for the task sequence modeling. We introduce two pseudo-states, start and stop state, to define a finite length task sequence model generator. Each Markov model are described by their transition matrices. Distances between two Markov model is defined as the Frobenius norm of the transition matrix differences. Using the same distance metric, we discovered the explanatory factor. We recursively partition the dataset on the basis of ranked explanatory factor to derive a conditional task sequence model. After deriving the factor dependency graph, we train the hierarchical Bayesian model. The Bayes model estimates the parameter for conditional distribution by recursively partitioning the data in factor dependency order. Using the parent node parameter estimate as prior, it updates the estimates at the child node. Such training ensures robust estimate of the system parameters. Thereby, for a given number of expected service requests, we first produce an expected service request types that corresponds to different process operating characteristics. For each service request types, the task sequence order is generated. An activity sequence is generated for each task using hierarchical Bayesian model. For each activity, we produce an unbiased resource demand estimates. Finally, the resource demand estimates are aggregated to service request level and reported. To test the effectiveness of the modeling framework, we have created a simulator for storm outage data. The simulator is initialized with a number of locations, and for each location the maximum number of service requests per request type, number of associated task types, and activity demand distribution. Using discrete event simulation, the simulator produces a storm outage data log. We partition this simulated data into training and test dataset. We train a model using training dataset and use test dataset for the validation. The model prediction on the test set closely matches the simulator output. The proposed model essentially carries out factor-based resource demand prediction. We have carried out a comparative analysis of the proposed model with XGBoost based model. XGBoost is a gradient boost based state-of-art algorithm known for its prediction accuracy for regression tasks. We have used all available factors to train the XGBoost model. We have used the simulated storm outage data described earlier. Though the training and prediction time for XGBoost model is much faster, our proposed model produces a much accurate resource demand estimates. To learn more about our work, please go through the paper titled Robust Resource Demand Estimation Using Hierarchical Bayesian Model in a Distributed Service Systems, or mail me at sumanim03@in.ibm.com.